Hey, here's our fifth example of how to apply Newton's second law to different kinds of problems. Now, when you first look at this, you go, wow, what's going on here? But realizing that there's no friction between the 4 kilogram mass and the incline, and there's no friction between the 8 kilogram mass and the 4 kilogram mass, it's really not that difficult of a problem. You'll see that's very similar to what we've done before. Now, in a later example, I will show you how to do this when there is friction between the masses, and then, of course, things change a little bit. All right, again, we're going to look at this as a whole system. All the forces acting on the system. The two masses are connected by a single string. Of course, the tension on both sides of the string would have to be the same. But at this point, we're simply going to just find the acceleration of the system. Now, since the 8 kilogram mass is bigger than the 4 kilogram mass, I would expect this 8 kilogram mass to be sliding downward and the 4 kilogram mass to be sliding upward. And I believe that the acceleration would go like that. So that would be a good assumption. We can kind of work that out by putting some forces in here. So here we have the weight of the second mass. This is m2g. And here are the perpendicular components and the parallel components of m2g. So this would be m2g times the cosine of theta. And here this would be m2g times the sine of theta. I'll use a different color for the second mass, otherwise it gets a little messy here. So this would be the m1g, the weight of the heavier mass. Obviously, I indicated that with a longer vector arrow. Then here would be the perpendicular component to the incline. This would be m1g times the cosine of theta. Notice the angle, of course, is the same. This here would be the m2g times the sine of theta. And you can see that the m2g sine theta is bigger than the m1g. This should be a 1, not a 2. Okay, there we go. So the m1g sine theta is bigger than the m2g sine theta. So if these are connected to each other, this one would be pulling harder than this force. So you can see that, again, that would give you the impression that that would be the motion. The perpendicular components, and I should put a little arrow on here, there we go. The perpendicular components are going to be canceled out by the normal forces. There is a normal force, or the reactionary force, the m2g cosine theta, so let's call this n2, and here's the reactionary force to the m1g cosine theta component, so let's call that n1. And notice that this will cancel out this force, and this will cancel out this force, and that leaves us, of course, with just this force right here and this force right here acting on the whole system. Now, I would say that this will be aiding in the acceleration and this one will therefore be opposing the acceleration. So when we use Newton's second law, we can write that F net is equal to mass total times acceleration, or solving that equation for the acceleration, we will get acceleration is equal to F net divided by the mass total. And again, F net will be made up by all the forces aiding the acceleration, which would be this component right here, which is m1g sine of theta, minus all the forces opposing the acceleration. That's this one right here, because notice this one will actually try to pull this mass upward by the weight of this one right here. So this one wants to slide this way, pulls on the string, tries to pull this one up, but this one is bigger. This one will pull this way, pulling that one up in the end. So this will be m2g sine of theta divided by the total mass, which would be m1 plus m2. All right, so this one aids in the acceleration. This one opposes the acceleration. That makes it a plus and a minus force. Plugging in the numbers at this point, m1, that would be 8 times g, 9.8, times the sine of 30 degrees, minus m2, which is 4, times 9.8 times the sine of 30 degrees, all divided by 8 plus 4. Again, I left the units off because it makes it a lot quicker and cleaner to work with these numbers. Now, notice that we're looking for accelerations. The units will be meters per second squared. So we got 4 times 9.8 times 0.5 divided by 12. And the answer is 1.63 meters per second squared. That's the acceleration of the system. Of course, what that means is that the 8 kilogram mass will be accelerating downward. The 4 kilogram mass will be accelerating upward. And that's how you do a problem like that.